much about large language models all the time, but we rarely stop to look at the literal first step of how they actually process information. We've got a really great roadmap for this explainer. We're going to kick things off with the basics of tokenization, then look at the types and mechanics, explore the bridge to embeddings, uncover some hidden costs and biases, and finally wrap up with security risks and a summary. All right, Section 1, the basics of tokenization. So, I want you to ask yourself this. What actually happens when you type a prompt into an AI? You probably think large language models just read words exactly like we humans do, right? You type a sentence in, it reads the sentence. But no, they actually read something entirely different. They don't process language as some fluid stream of letters. They require a highly structured translation first.
Enter tokenization. This is literally the critical first step in natural language processing. It's where raw, continuous text is broken down into discrete, machine-readable units that we call tokens. And the absolutely crucial point here is that tokenization dictates a model's capacity, its sequence length, and its overall processing efficiency. It basically tells the model what kinds of things exist in its universe. If an AI doesn't have a token for something, it is really going to struggle to predict it.
Moving right along to Section 2, types and mechanics. How are these tokens actually built?
Engineers actually face a really fascinating trade-off when they decide how to break text apart. First, you've got word tokenization. Sounds obvious. Just split the text by spaces to get natural boundaries. But the huge disadvantage there is that you need a massive, totally inflexible dictionary for every single word in existence. Then, you've got character tokenization, which fixes the size issue by just splitting by individual letters. It covers everything, but it creates ridiculously long, inefficient sequences, and single letters don't really carry much semantic meaning on their own. So ultimately, the industry settled on subword tokenization. It balances vocabulary size and flexibility by creating frequency-based chunks. It's honestly the perfect middle ground. To understand how these subwords are actually created, we can look at a widely used algorithm called byte pair encoding, or BPE. It's essentially this greedy frequency loop. First, it starts with single characters. Next, it sweeps through the training data to count adjacent pairs. Then, it merges the most frequent pairs into a brand new token. It's a lot like atoms forming molecules. It just repeats this process over and over until a set target vocabulary size is finally reached. The massive benefit here is that it retains real linguistic patterns, like common prefixes and suffixes, which keeps everything highly efficient.
Section 3, the bridge to embeddings. How do we actually get from discrete tokens to math? Okay, this is where the real magic happens in the AI pipeline. Your input text gets tokenized into those separate chunks we talked about. But the real secret sauce is the embed stage. Those discrete tokens are mapped to distinct mathematical vectors called embeddings. These embeddings live in a high-dimensional space that allows the language model to calculate the exact mathematical relationships between words. That is literally how the model understands semantic meaning and predicts the next output. Tokenization is the essential bridge that makes the whole thing possible.
And you know, developers don't have to build this from scratch every single time. They rely on standard open-source tools and libraries to handle this complex conversion. For example, OpenAI models often use TickToken. There's also SentencePiece, which is fantastic because it operates directly on raw text and bytes, treating spaces as just another character, making it an absolute game-changer for languages that don't even use spaces between words. Then there's WordPiece, heavily used by BERT models and various Hugging Face tokenizers. Each tool is perfectly tailored to fit different language model architectures.
Section 4. Hidden costs and biases. Let's talk about the actual price of efficiency.
There is a major structural disparity hiding in plain sight within modern AI. Because most popular tokenizers are trained on English-centric web data, they are highly optimized for English text. We're talking roughly 1 token per word, which is incredibly cost-efficient. However, for non-Latin or Asian text, the tokenizer doesn't recognize those patterns as well. It's forced to break the words down into many tiny character tokens. You end up with multiple tokens per word for the exact same semantic meaning, making it massively, massively inefficient.
Astoundingly, this leads to a direct financial penalty. Research shows that users typing in Abugida scripts, which are used all across Southeast Asia, pay on average 1.68 times more in API costs compared to English users for semantically equivalent prompts. Since the tokenizer dictates the sequence length and APIs charge you per token, equitable tokenizer design is literally a matter of financial fairness.
And get this, the costs can spike for other weird reasons too. Take the multiplier 2.09 times. That represents what happens during something called tokenizer drift. If a tokenizer experiences an accidental bug or some malicious change in its configuration, it can totally lose its efficient merge rules. When this happens, token counts can instantly explode by over 2 times. Your AI model hasn't changed at all, but suddenly your context window shrinks, your CPU usage spikes, and your server bills literally double without warning. Crazy, right?
Section 5. Security Risks and Summary. Let's look at some vulnerabilities.
This specific vulnerability is known by researchers as a glitch token attack. Usually, a normal prompt generates a perfectly coherent response. But if you introduce a glitch token, which is just an unexpected or anomalous string of characters that the tokenizer processes bizarrely, it completely shatters the model's semantic understanding. Because the embedding vectors get totally scrambled, the model suddenly spews out completely irrelevant output. You could ask it about a game studio and it starts giving you a recipe for curry. It's a fascinating and honestly dangerous vulnerability.
So how do we fix this? To prevent these issues, and to stop things like economic denial of service attacks where malicious users try to run up your server bills with bloated tokens, developers have to take decisive action. You have to rigorously lock down your tokenizer artifact hashes to ensure they haven't been tampered with. You absolutely must monitor your production tokens per character ratios to catch drift immediately. You need to set hard caps on input tokens, and above all, secure your AI supply chain.
As we summarize today's explainer, consider this crucial quote from the research. How tokenization is carried out across languages shapes the economic accessibility of multilingual models for underrepresented language communities. Tokenization isn't just some quirky engineering step. The seemingly simple act of chopping up text dictates the fairness, the literal financial cost, and the overall safety of our global AI infrastructure.
I'll leave you with this final thought. What hidden biases might be lurking in the tokenizers you use every single day? As you interact with large language models going forward, stop and ask yourself how the invisible mechanics beneath the surface might be quietly shaping the AI's output, its cost, and ultimately its worldview. Thank you so much for joining me for this explainer. Keep asking great questions, and I'll catch you next time.